Okay, so what we did last time, and I would go with. Can you see the what?
Yes, yes, sir.
Okay, so now with the light has but two nature. One is the wave nature, and another is the particle nature. Okay,
Yes,
so wave nature and the particle nature, and the humans are giving this nature and everything because light is doing its job what it can do, but we
yeah.
want to understand why this is happening and how that is happening and how to convert that all the understanding into a mathematical model to further calculation and derive some application out of that. We need to have a either go with the wave nature or the particle nature depending on the certain kind of thing what the light is doing. For example, if you have something like even propagation. Okay, the propagation, we need the wave property. Do you get that? And also some
Yes,
call that as a transmission. Transmission, because in optical fibers and everything, we put it as a transmission. And another, the next one from this, when it propagate, it may hit a surface or something like that. Then the surface is very rough. Then it goes through scattering.
yeah.
Scattering is also a wave property. And let's say if it is a transparent one, then it goes through refraction.
Reflection. Yeah.
Refraction, and if it is a not a rough surface, very smooth and very reflective, then we have a reflection.
This,
Reflection. And apart from that, we have a set of other things which we call bending of the wave around the corner is called a diffraction. And in the sound waves also, you need to understand what is the diffraction. Is that okay? And then when it is diffracted, there could be more, more sources which may have the same light get diffracted or something. So if there are more waves, then they interact. We call that as a interference. So they interfere, and we need to understand all this thing using the wave property. Using the particle nature, what is the first thing you know about particle nature? What kind of phenomenon we can explain from there? You gone silent. Hello?
yes, uncle. Yes.
Yeah. So do you think any property or anything?
Absorption. Okay.
Yeah.
Yes.
And emission. So this is a very important thing, like even the source of the light, where the light comes from, actually it is emitted by some hot body or a radiating atom or a molecule or something like that. So then
Yes.
the inner bound electrons comes into picture. So a photon, so the particle nature, we call that as a photon. Okay. So the photon, the sound itself, the word itself is coined like a particle ending with a TON, like an electron or proton or neutron. So the whole idea is how this wave packet of energy, a small tiny piece of energy absorbed by a atom, so that the atom get excited, the electron in a lower energy level jump into the higher energy level. Completely the light wave is gone, but the energy is attached with the atom. Do you get that?
Yes, sir.
And that is what the particle, without with the wave nature, we cannot explain that because wave is completely disappeared that, but the energy of that particular small piece of that wave, which is called the photon energy, that is available in the atom in the form of the electron is jumped to the higher energy level, and it cannot stay for very long time. It will jump back to the original energy level. In doing so, it can emit back that particular photon. Then that is called the emission. So those kind of things cannot be explained by wave property. So that's what
Okay.
basic difference between the two. But light is doing what it can do. When it interact with other light, it will work like a wave, and when it is interact with atom or molecule, then it is behaving like a particle. And for mathematical modeling and understanding, that is helping us. Is that okay?
Yes, sir.
So where we can start? I mean, we can start with the refraction and look into the Snell's law and complete that. And is the fiber optics included in the portion?
No,
No. So
no.
how about Snell's law?
Snell's was
Snell's
cyanide.
law is there.
Yeah.
Okay. Can we first complete that?
Yes, sir.
Okay. So now what we are saying that when it is propagating, so in the medium, so medium is, for example, it could be vacuum or it could be air itself, whichever is transparent, we are called that as a medium, so that the light wave can propagate in there. It could be glass or it could be water. So you know what are all the things what we are talking about here. So now what is the thing we call that as a wave? This particular light wave or something like that, they comes under the electromagnetic wave. Is that okay? Electromagnetic wave. So the electromagnetic wave got both electric and magnetic. So we have electric field. You remember we studied about electric field long time ago. Is that okay?
Yes, yes.
And there is a magnetic field. So when we studied these two things, I mean, I don't know whether we covered that bit. Actually, under the electric field, this is coming from the charges and then the battery and the capacitor. All these things can be understood only this thing. So all these things, when it is electric field, when it comes to even the basic Coulomb's law and to calculate the electric field, the epsilon comes into picture, which is called the permittivity. Is that okay?
Yes, sir.
Permittivity. And I recall this one, if you still remember, always the epsilon naught is the vacuum permittivity.
Yes,
Vacuum,
yes.
okay, vacuum permittivity. And we compare that with any other thing can be written as, in comparison with the epsilon naught, they may have a higher value multiplied with that. So we call that as a relative permittivity. Is that okay? So this is
Yes, sir.
relative permittivity. So similarly, so this is under our the electric property of the. So these things are coming from the medium or the material. We understand that.
Yes, sir.
So when the electromagnetic wave, which has an electric field, when it is propagating or getting refracted or whatever it is, when the medium will respond to that in terms of it will talk to it through its epsilon value. Similar to that, for the magnetic field, what is the equivalent for the magnetic field?
Mu, yeah. Yes. Mu by
Permeability. Is that okay?
permeability. Yes.
Similarly, there is a mu naught, and that is actually for the vacuum, and I will write that as a 4 pi into 10 to the power of -7 Henry per meter. Okay. And here the epsilon naught is going to be 8.85 into 10 to the power of
-12.
12 farad per meter. Always the units are very important. When we have that, it will be very handy. In case we don't know how to solve a problem or something like that, we can cook it out of the units. Is that okay?
Okay.
So now the mu will also be expressed as a mu r, relative permeability multiplied by the vacuum permeability. Is that okay?
Yes.
All good. So why we are bringing this when we are talking about the wave and electromagnetic wave interacting with the medium? So let's say take the case of vacuum. So the electromagnetic wave is this is the light, which is the electromagnetic wave. So this has to go through the medium. It is traveling. When it is traveling, it is covering distance using some time for that. Do you get that? So there is involved the traveling distance, and that is depending on the time. Obviously, the quantity which is relating both of them is going to be the speed or the velocity.
Yeah.
Velocity or the speed. So now we are going to say that if this guy has both electric field and magnetic field, both are vector quantities, they both are orthogonal to each other. I don't know whether they have drawn any diagram with the electric field, magnetic field, something like that. Like
No.
along that, there is a sine wave for the electric field. And then perpendicular to that, horizontally, you will have a...
Okay, yeah. Yes, uncle. Yeah.
Okay. You see, it's very simple to forget things and not to connect things, but it is our job to, whenever we learn something, even the teacher may not know that, even the textbook may not explain that, but it is our job to connect them. Otherwise, it will become a humongous job to remember all these things isolated. You get that?
Yes.
If you see any McGraw-Hill book, always this diagram will be on the front page. Have you seen them?
Okay. No.
So nowadays, these publishers are almost gone. The India people, nobody use the McGraw-Hill books.
I'm not sure of the name, uncle.
Yeah, McGraw, McGraw-Hill publishers.
No.
Publishers. Okay, so they have a fantastic textbook. Maybe when you go to the university or the college, you will start knowing about that. So the wave, the electromagnetic wave got this. Now, this is going to talk with the vacuum with its epsilon naught. Is that okay?
Okay.
And the electric field will talk with the... So this is simply like, what is the one which is making them to move from one point to the other? So only in terms of epsilon naught and mu naught they will talk. Now comes to the beautiful expression. So we can calculate the velocity, which we call that as a V naught. The vacuum velocity is nothing but 1 over square root of epsilon naught mu naught. Is that okay?
Yes,
And we call that as the constant C, which it will come to. So this is actually equal to 1 over, if you plug it in the value, 8.85 into 10 to the power of minus 7 multiplied by...
minus 12.
Sorry, minus 12. Okay. Good. And this will be 4 pi into 10 to the power of minus 7.
Minus.
Of course, if you put even the unit, this will be farad per meter, and this will be Henry per meter. This everything will simplify approximately to something like 2.9989 into 10 to the power of 8 meter per second. We approximate that C is approximately 3 into 10 to the power of 8 meter per second. Is that okay?
Okay, yes.
Okay. So now this is good. This is for the vacuum. But let's say we go to some other medium. Let's take it as a air, or it could be a air, or it could be a glass or something. Then we can calculate the velocity in that medium definitely by the same thing what it is. Okay, I will give the name of the scientist who derived this. This is James Clerk Maxwell. Okay, James Clerk Maxwell. He's a Scot, and he lived very nearby here and worked at our university. Okay, and under his, we have the Maxwell's equation. He derived the equation. Okay, so this is calculated by whatever the permittivity of that medium. If it is air, then we should use the value of the air epsilon here and mu here. Is that okay?
Okay.
And now if you try to look into it, this is always expressed as epsilon or epsilon naught multiplied by mu or mu naught. Okay, so this can be split into 1 over epsilon naught mu naught multiplied by 1 over square root of epsilon r mu r. Is that okay? And we know that 1 over square root of epsilon naught mu naught can be written as a C, the vacuum speed, and we define a new quantity called refractive index, which is nothing but 1 over square root of epsilon r mu r for all the... Is that okay?
Yes, sir.
Okay, so that thing makes the whole thing because of these two things. So the velocity in any medium can be written as 1 over, I write it again to plug it in easily, epsilon naught mu naught multiplied by 1 over the, okay, that is where I want to write it and then make the correction. So this is wrong. So this is actually, is there a eraser I can go about or? Okay, so this is wrong. Actually, this is a
Okay.
square root of simply the square root of epsilon r mu r. Is that okay?
Yes.
Not 1 over. So that this is square root of epsilon r mu r. This will become, the first thing will become a c over n. Makes sense?
Yeah, okay. That's why we get n is equal to c by.
Yes, exactly.
Okay.
You see that. So sometime that's why I write it again and then see that whether I'm getting the velocity in a medium is given by the maximum speed the one can have in the nature, that is the 3 into, nothing can go beyond 3 into the power of 8 meter per second.
Yes, sir.
This is called the refractive index. Let me write that. This is the refractive index. So the refraction comes here itself. Is that okay?
Yes, sir.
Okay, so the Ri, we call that as a Ri in short. Ri n is actually given by our C over B. Is that okay? It
Yes.
is always, the C will be always greater than the V, because this is the maximum speed in nature. So any other medium, the electromagnetic wave or the light wave will travel with a lower speed. So that means we can easily say that n will be always greater than or equal to 1. The special case is a 1. When you substitute in vacuum, we can say the n naught or something like that, which is C over C, which is the 1. Do you get that?
Okay. Yes.
So that special case equal to 1 is the vacuum. If you take a glass, it will be around 1.5. Water is also something like 1.35 or something like that. So different material will have different refractive index, and that can be calculated by square root of epsilon r mu r. Is that okay?
Okay. Yes.
So now we need to understand that something is going on. Like when it is traveling from one medium to the other, the speed will change. So when it is traveling from, so we can take different scenarios. So take the first scenario. Let's say this is a air and it is getting into a glass. Is that okay?
Yes.
So let's say a ray of light is traveling, and so when it is traveling in air, it will have its own velocity. I call that as a VA. Is that okay?
Yes.
Because that is, then automatically we know that it has a NA. So they both are related as VA is actually equal to C over NA.
Okay.
Immediately. So when we have all the understanding, immediately we can plug it in and start working on all the mathematical model. That means equation will plug into. So now to understand what is happening, we are going to draw a normal. We call that as a normal because it is 90 degree.
90 degrees to the surface.
Yeah, to
the medium.
surface. It is called the interface.
Okay.
Interface. Whatever the separating line or the plane, because it is a 3-dimensional thing, but we are just drawing it on a 2-dimensional diagram. So it is an interface is a plane which is perpendicular to the, the normal is perpendicular to the interface. Normal is also, it looks like a line, but we can think like it is actually a plane. Is that okay?
Okay. Yes.
Then first thing what will happen, because it is definitely there will be a reflection. Okay. So
Okay.
will be reflected ray. So we call this as the incident.
That depends if the medium is like smooth, right? Otherwise, it won't. It will be like.
Yeah, that is taken care, because we are not now going into the scattering. Do you get that?
Okay. Okay. Yes.
I put the line, interface line, as a very straight line. If it is
Okay.
a rough surface, we need to say that the size of the pores are in the order of 1 over lambda power 4. So those scattering and everything, Rayleigh you study all those things, Rayleigh scattering, and it should be in the order of lambda power 4 and everything. Hello? I can't hear you. Hello?
Can you hear me now?
Yeah.
Yeah. No, uncle, we didn't.
So you don't study about those things, isn't it?
No. No.
Okay. So, but the scattering is actually called a Rayleigh scattering. Okay.
Okay.
So there are different kind of scattering. One of the scattering is called the Rayleigh scattering. So whenever a light ray which is going through a surface, or even in the medium, like for example, take air. Air doesn't normally have any uh, particles except from the basic gases like hydrogen, nitrogen, oxygen kind of stuff. But let's say if it is having some dust or cloud or something like that, like moisture or something, those particles will be of the size of order of that lambda power 4, the wavelength
Okay.
order. So whenever it is hitting those kind of object, then the scattering will happen. Okay. So that is why when it is raining, the whole area, the volume of the air in that place will be highly humid. That means lot of water particles are available. So the scattering will happen, and that scattering will go through the dispersion also. So there is another, I forgot to write that word here. Okay, dispersion is also a wave property. Without that, we can't explain that. Is that okay? I will add dispersion also into the. So I don't think you study dispersion, right?
Oh, we did. We did.
You study dispersion also?
Yes, uncle. That's why we learned it as part of ray optics. The prism.
Okay. Oh, prism dispersion. Yeah, okay.
Yeah.
So that is why we see the rainbow. Do you understand that?
Yes.
Because it different wavelength of the light will travel at different velocity also. So here we are considering that it is a smooth surface. That's why there is a reflected ray. And let's say there is an angle. Only if there is an angle, there will be this kind of refraction is going to happen. Okay, so now refraction will be obvious. So let's say this is the theta incident. Okay, so this is called the incident ray. Okay, so theta I, and then we will have the reflected one will be exactly the same angle. Is that okay?
Yes.
Okay, and then now there is a question, because it is going through, let's say the glass has a refractive index Ng, and let's say because of that we know how to calculate the Vg, which is given by C over Ng itself. Now here comes the bit of a question, whether it will go straight or it will trace a different path. We get that. So if this interface is not there, it would have gone straight, but the glass, we definitely know that the Vg is going to be less than Va. Do you get that? Hello, your voice is already, sometime I can't hear you.
Can you hear me?
Yeah. But
Okay.
did you answer bit a second before?
Yes, uncle, I told yes.
But that was not heard at all. Why it is so?
Okay.
Okay, I'm not sure. Okay, so the velocity in the glass will be less than the velocity in the air. Then, I'm not going to do all the optics, geometry and everything. It is going to get bend towards the normal.
Towards the north.
Yeah, so we just take it granted this is what is going to happen. Okay, so because we can, that is not a very difficult thing, but let's take it as this is going to go towards the normal. So this is going to be our angle of refraction. Okay, so now we have a job to do. So we can, I did not explain why it is bending, because it needs to reduce the velocity. Only by bending towards the normal, it can reduce the velocity. Now we can do a bit of a geometry using trigonometry, everything. Eventually, it turns out to be, so at your level, school level, 12th standard, they tell that there is a Snell's law. So he is the first scientist who did this calculation using the simple trigonometry. And eventually it comes about, it went from one medium to another medium, right? So stress
Yes, sir.
is easy to write. You write the one medium thing on one side and the other medium on the other side. That will be perfectly okay. So it came from air to glass. So write the refractive index of the air and sine of whatever the angle made by the ray with the normal in that medium should be equal to the refractive index in the second medium, that is glass, multiplied by the angle made with the normal in the second medium. Is that okay?
Yes.
So this is easy to, you don't need to memorize something like this. This is like a very systematic thing. So keep one medium on one side of the equation, other medium on the other side, then we can simply write this. Do you get that? Okay, so try to remember this, then you don't need to worry about. Now we can immediately say, let's say a case of, for example, if it is coming from, I would write in generically N1 first medium sine theta 1 is actually equal to N2 sine theta 2. That become more
Okay.
generic. Is that okay? It could be from also we separate the medium as rarer medium and denser medium. So
Denser.
in this case, yeah, the air is here. When the speed can be higher than the other medium, we call the first medium where the speed is higher as the rarer medium.
Rarer,
Yeah.
whereas lesser is the denser.
Denser, yeah, this is a rarer medium. It's a comparison only, and this become a denser medium.
Yeah, yes, sir.
In the two. And let's say we change it to, for example, if it is going from vacuum to air. So now it is relative. This become the rarer medium. We get that? And this become
Yes.
the denser medium. Because the velocity of vacuum is going to be, which is our C, and this is our VA. Definitely the VA is going to be less than C. Okay, so that is why this become a denser medium. So like I put it in general, it could be air or glass or whatever it is. Okay, so water or whatever it is. So if you do the same thing in this case also, so definitely when it is coming and hitting, it will bend. Is that okay?
Yes, sir.
Okay, so now if you call this angle as a theta 1 and theta 2, and or if you want to make it as an incident and refracted also is okay, but I would call okay, or and refracted, and let's say this is our N, which is equal to 1. Is that okay? Vacuum
Okay.
refractive index. Okay, so because this is actually given by C by C. Okay. So now we know that this is actually given by VA is nothing but our, or whatever the velocity in that medium. I call that in general as a any medium or anything. Let's call it as a V itself. Is that okay?
Okay.
So V is going to be C over whatever the refractive index of this medium. So keep that in picture. Now we could easily write we know the general formula is N1 sine theta 1 is actually equal to N2 sine theta 2. Plug it in. N1 is our 1 in our case, vacuum. And then multiplied by sine of theta incident is actually equal to N2 is our general refractive index of the medium, second medium. And then this is a sine refracted angle. Is that okay?
Yes.
Okay, so then we can rearrange the refractive index of any medium can be calculated by the sine theta I. So this should be in vacuum actually. Then only this we can put the sine theta R. Is that okay?
Yes, sir.
So if this is the case for, so now what we could do, yeah, this is okay. So you're okay with that?
Yes, sir.
But if it is going to be not a vacuum, then we should not substitute the 1 here. You should substitute
Yeah,
the
it'll be N1 and N2.
yeah,
Whatever
N1,
value.
N2, and that will be a relative, the ratio between the one to the other. Okay. So I will write that generic one also. So if you say that it is a going from N1 and the sine theta I going to a second medium refracted as a sine theta R, then we can say that N1 by N2 will be equal to sine theta R by sine theta I. Is that okay?
Okay, yes.
This is how n2 comes to the denominator here. Theta
Yeah.
sine theta I comes to the denominator on the other side. Okay. Some student used to do mistakes with so when you write it in the ratio like that, we may get confused. But start with the one which is from one medium to the second medium. Do you get that? Then it will be easy. Okay.
Yes.
Okay. So now, as we learned the refraction, I don't think we need. Is there anything else you learned in the refraction? Okay, so some other common mistake done by, let's say I give you a small problem to think about, to work on. Let's say there is an interface between vacuum and some glass. Okay, so definitely we are going to have a, so let's say they are given you that this is our 60 degree, and let's say it is going to not going to be going straight, it is going to bend. And let's say they give you this as the some question mark. They are asking what is this angle. So they give that NG is going to be our, let's say 1.5. So this is the problem.
Yes.
How to go about it?
Okay. So we know that sine I is 60.
You mean theta
Can you
I?
hear me?
Yeah, you mean theta I.
Yes, uncle. Theta I is 60.
Okay, can you look into the diagram and see that whether that is the angle we call
Oh,
that
no,
as
no, no,
theta
no,
of
no.
incident. You see that
No, that's not
this is
theta.
very
No,
common.
that will be 90 minus 60. That 30
Yeah,
is theta.
exactly. So this is a 90 degree minus 60 degree. This is very important. Do you get that?
Yes.
Okay. And then, okay, now you got the theta I. Then,
Theta R we need to find, but we know that N
what
NA will
is
be
that?
1.
Yeah,
NV.
first write the generic one. N1 sine theta 1 equals
Okay.
N2 sine theta 2. So go with that and then start plugging in what is what in this. So in this, our N1 is nothing but 1. And N2 is our NG.
1 point.
Yeah, that
Okay.
is given as a N2 is given as a 1.5. And that means we now know everything in here. And also we can say that our theta 1 is our theta I that is given to us, which is actually our 30 degree. So plug in this value, and this value into the equation. So we will have only one unknown, that is 1 multiplied by sine of 30 degree is actually equal to the N2 is our NG, which is 1.5 times sine theta R. Is that okay? So theta
Yes,
2 is going to be our theta R, which is the question mark. What is the refracted angle in the glass with the normal? Okay, so this is going to be 1 over 2, and 1.5 can be written as a 3 over 2 multiplied by sine theta.
Yeah, 1 by 3.
Okay. Sorry, it's a 1 by 2 because I'm going ahead very quickly. So this will be factorized. Is that okay?
Uncle, it's 3 by 2 only, right? 1.5 is 3 by 2.
Yeah. Sorry. So
Yeah.
that will be our
1 by 3 will be sine.
theta R will be 1 over 3.
So sine inverse of
Yeah.
1 by 3 will be equal to 3.
Yeah, apply the sine inverse on both sides. Then the sine will cancel on one side, and we need to use the calculator to find it. The mode should be in degree because they started the whole problem in degree. So you need to use the degree mode. If the problem is with the radians, you should give the final answer in radians. Is that okay?
Okay.
So
Yes.
we did this purposefully to cancel the sine inverse and the sine. So theta R will be equal to sine inverse of 1 over 3. Can you plug it in and give me the value?
Yeah, 1 second. Uh, 17.45.
Are you sure?
I use the calculator.
Yeah.
So
Can you do it
it's
again?
yeah, okay. 1 by 3 will be 0.33.
Sine inverse.
So 0.33 sine inverse. Sorry, 19.2.
19.47. 19.47 degrees. Do you get this?
Okay, yes.
12 actually. Careful with that because you might have done lot of hard work in doing up to that stage and you make a
Yeah.
mistake, then they will take away marks for that.
Okay, in these exams, obviously we don't have calculators, so they'll give the value in the question.
Okay.
So
So-
if they don't give the value, we can just leave it as sine inverse of 1 by 3.
Yeah, but so you no, none of the exam use the calculator?
No, we don't have a calculator for any exam.
Okay. Okay then. Okay. Okay. So now we are here. So we solved this problem. Let's get to. So I stopped the. I hope you can deal with that. So I know that a lot of students do the mistake when the angle is given with respect to the interface. Okay.
Okay.
So
Yes.
they don't convert that for the normal, but careful with that. Okay.
Yes.
So we need to finally, when you get an answer, now you see 19.47, that should make sense because the incident angle with the normal is a 30, bending towards the normal. This angle, we are saying that it is a 19.47 degree. That is okay because the 19.47 is less than the 30 degree. Is that okay?
Yes.
And we should also know how to check this because you can calculate using the 19.47 and the 30 degree using the Snell's law and check the refractive index of the glass is coming to 1.5. Is that okay?
Yes.
Okay, that is another way to check that also. Okay, let's move on to the next concept, whatever we want to learn today, and use the rest of the page also. Why not? So let's go to, so we have seen the reflection and scattering also we discussed. And so you want to see the dispersion or we go to the interference? Hello?
Yes, uncle. Can we do dispersion?
Dispersion. Okay, let's come. Okay. If your time is there, then we continue with the other thing. Otherwise, next time we will look into the
Yeah.
Okay, dispersion. Okay, so far what we have seen, when it is traveling from one medium to the other, something is happening. So we call that as it is a refraction if the surface is smooth or something like that. And then all okay. But there is a property attached with the signal itself. Last time, the light wave signal itself, remember last time, it has a wave property. Do you get that? Then only we can explain that. So the wave itself, we have something called, let's say you take this as remember the last time what we did with the circle and the sine waveform and everything, remember that?
Yes, uncle.
This can be written as a, let's say I write it as a, for just for curiosity to check this, cos of omega t minus theta. Look at the diagram. Let's say this is our time and this is our whatever the lowercase a of t. So we are saying that this should be our values for the a and this is our function. Do you get that? This is our a of t. Tell me what is the theta value? Look at the diagram and look at the function. Function says is a times cos of omega t minus.
Okay. Yes.
But the diagram looks like a cos.
One second.
Can you use
no,
the
no.
in the yeah, okay. Then how to extract the theta? What is happening here? Because
It's
the point,
telling 0 is almost like a sine wave.
Yeah, when time t, yes, it looks like a sine wave, but we can use the information. When time t equal to 0, the a is actually a of 0 is a 0. Do you get that?
Okay, yes, uncle.
Okay, we can plug it in. That will help the problem solved. All we are saying is A times cos of our whatever the omega multiplied by 0 minus theta is going to be our
0.
0. Is that okay?
Okay, yes.
So this is going to be our A cos minus theta
Minus theta.
is going to be 0. So that is nothing
Cos
but
of
cos
minus
of
theta.
theta minus
Theta,
theta
yeah.
and plus theta are 1, right? Okay, we can put the
Yeah.
minus theta here for you. That is going to be 0. Is that
Yeah,
okay?
okay.
So now comes the, so
Theta is 90.
it leads to theta is going to be cos inverse of our 0, which is going to be, first answer is a 90 degree. Is that okay?
Yeah.
Also equal
Yes.
to 0.2. So keep it handy that, it's about our observation. Are we looking into the information given there and get a feel about that and everything? Then that will obviously, it will click the right neuron in our brain to what could be used to get a problem solved or something like that. Is that okay?
Okay, yes.
So you see the theta is calculated now. Then we know that t is the independent variable. Okay, we know that how it works and everything. So what is this is called? This point is called, what is the length of the time here?
2. Yeah.
What is the definition? I mean, because we are learning physics, you need to use both the physics and the math.
T equals T.
Is capital T. Do you get that? It's called the
Okay, yes.
you get that?
Yeah.
So this is the period, one period.
Yes, yes. Times.
How
Yes.
to look for one period is, we started at that point where the wave crossing the 0 and going, just before that it was negative and then it was going to positive. So look for the same kind of scenario. It's the same phase. Exactly what is the exact, here also it is 0, but it is going from positive to negative. It's not the same instant. Do you get that? But if you walk
Okay, yes.
along, this is the instant where from the negative, it goes to the positive and it crosses the 0. So that becomes the period. Then why I am considering this now, because this omega is the another parameter that we need to understand. Theta is fixed. Now we say that omega can be written as, in that t period, it would have completed 2 pi radian. So the omega is the angular velocity or the angular frequency, which is given by 2 pi over t. So that means that can also be calculated if we know the numerical value for the t. Is that okay?
Yes.
And then how about the A? That is the
A
maximum.
will be the amplitude. So that, yes, uncle.
Maximum. It's called the maximum.
The maximum
We are
amplitude
using
will
that positive maximum, negative maximum amplitude is
minus.
A. So that is how we extract the wave form in the algebraic form or in the functional form to the geometry, or from the geometry we can derive the parameters out of that. Is that okay?
Okay, yes.
That could be used in the maths or in the physics problem or something like that. Now let's come to the interesting point. Let's say there is a medium here, and that medium there is a wave propagating. So this will have its own velocity in the medium. Let it be. But this velocity is going to talk to the medium. The wave velocity is going to talk to the medium or defined by the medium using its refractive index, isn't it? Because we calculate velocity is nothing but C over N. All good. But velocity is not the only property of the incoming wave, right? So we need to ask the question, what is its amplitude? What is its frequency? What is its constant phase angle? Do you get that?
Yes.
Because they may have influence on the refractive index. Do you get that? It's not that only the velocity is determined by the n value. N value is actually, really speaking, it is a function of omega. That is the reason why it is determining the velocity. Do you get that?
Yes.
And also it is a function of intensity, which is nothing but the mod of the amplitude, peak amplitude square. But this is called the intensity of the light. Intensity. But this is all comes to something later when you study in physics or something in future, in engineering or optics or something. this whole thing, n dependency, n of depend on the intensity is called, comes in the nonlinear optics. Is that okay?
Okay.
I just to give a idea, nonlinear optics, but in the A level, I mean the 12th standard, I don't think they will go there, because they are not, you are not studying about any laser light propagating in a medium.
No,
That
no,
will
no.
that will introduce that. Do you get that?
Okay.
But let's stop that for 12th standard. 12th standard, we stop it. N is a function of omega. Is that okay?
Yes.
So there comes the beauty. That means, let's say the incoming wave itself. So let's say we are talking about take the medium interface, and then with the normal, there is a light ray coming in. Let's say this is our vacuum. And the incoming wave, let's say it is not a single frequency. Let's say it has omega 1, omega 2, for example. Okay. Here also there is a vacuum refractive index, which is a 1. Do you get that?
Yes.
So that means we are saying that for the n of omega 1 is also 1, the n of omega 2 is also 1. Do you get that?
Yes.
That means what? The velocity of that is the velocity of omega 1 in the vacuum is going to be c, no problem. The vacuum velocity for the omega 2 is also c. Meaning, let's say from the sun to the earth, all the wavelength, all the frequency, all of them will be traveling at the c velocity. Is that okay?
Okay.
So there is nothing called different velocities for different frequency of the light or the wavelength of the light happening in a vacuum. But let's say this is a medium which is a n is greater than 1. That means it is not a vacuum. Then also we need to include that n is a function of omega also. That means when the n of omega 1 will be different from n of omega 2. Do you understand that?
Yes.
Okay. So the n, the n, just for understanding, I will just draw it. It will look like this. Okay, something like that. So somewhere for the glass, the visible region will be here. Is that okay? So this will be in terms of lambda, the wavelength, and this is our 700 nanometer, and this will be our 400 nanometer. So this is our red, and this is our violet. Do you see that? So we will have the BIB GR. Is that okay? So different wavelength, different color is sitting in this. So this is the n value. So if you take the red color is passing through the glass, then this will see this nr value. Is that okay?
Okay.
And violet is passing through the, so this will be the n violet. Do you see the variation in the refractive index?
Yes.
So this will cause the dispersion. So what will happen? Let's say, for example, the omega 1 is our omega R, which is our red color. Is that okay? This is the red color. And there is another color, which is our violet, for example. Omega 2 is our omega violet, which is the violet. Okay. So as they have different frequency or the wavelength, we need to look into the chart or something, or in the exam, they may give the value. Then that will help us to understand what will happen also. So let's say, okay, so the average value or something is here 1.5 means the NR will be lower. So this could be something like a 1.445, for example. Is that okay? Or consider that a 448.
Okay.
This could be like a equal to 1.49, for example. Is that okay?
Okay.
It's a small value, but
Yeah.
Okay, for understanding, I will go higher value, 1.52, a material like that. Is that okay?
Yes.
So now tell me the bending. So we are going to draw. This is not going to travel along the same path. It is going to bend towards the
Normal.
normal. Okay. But we know that the angle is related to the, this is actually the theta I, for example. Now, there are two wavelengths corresponding to the omega 1 and omega 2. And I forgot to tell the relationship between the two. Like, okay, I will give you a bit of a clue to think about and solve the problem. It will bend at two different angles. Do you get that? Okay, so one will go omega 1 and omega 2 will get different path. Reason being, the medium is giving different refractive index. Do you get that?
Yes, sir.
Because we know that N1 sin theta 1 equal to N2 sin theta 2.
Sin theta.
This is generic one. This is Snell's law. Is that okay? But now we have, okay, this is actually 1. So we know that sin theta I is actually equal to, now we have two equations because this has to be split into n red sin theta red. Do you get that?
Yes.
And you will have a sin theta I equal to n violet sin theta violet.
Okay.
So now use the value of the NR and NV and then work it out in these two equations so that you will come to know which one is bending more towards the normal and which one is bit away from that. Do you get that?
Okay. Yes.
So that angle, because we are talking about two different angles. Do you get that?
Okay. Yes.
There. Okay. So I will leave it as a homework for you to think
Okay.
about and work it on. I will quickly. You have another class starting now, right?
Yes. Yes, sir.
Okay, I will quickly stop here, but in the time we say that this is one period, right?
Okay.
Okay. And also, if it is a space, then we call that the same thing as a wavelength. Do you get that? Is that okay?
Yes, sir.
Okay, so now when we say that velocity can be calculated by the distance traveled by the time, now we know that this can be written as a lambda times 1 over capital T. This 1 over T is the F. So V can be written as
lambda
F. So this is not a memorizing formula. This can be understood from the wave nature. Is it okay?
Yes. Yes.
Okay, dear. Okay, I stop here and then we'll
Yeah.
meet next week. Okay.
Yes.
Take care then.
Thank
Bye.
you.
Yeah. Okay.